Usually when we talk about a medical diagnosis, there's this expectation of like absolute precision.
Right. It's very binary.
Exactly. Almost like engineering. You break your arm, the x-ray shows that jagged white line, and the doctor just points and says, there it is.
Yeah, broken or not broken, it's completely visible.
Right. It's clean and it's comforting. We really like things to be visible, to be neatly categorized.
Yeah.
But then you step into the world of network engineering, and suddenly that x-ray machine is pointing at something completely invisible.
Oh, absolutely.
We are looking at a diagnostic landscape of digital handshakes, electrical pulses, and, radio waves,
Yeah,
which is honestly a bit magical when you really start to think about it.
it really is.
So welcome to today's deep dive. We are looking at the invisible plumbing of local networks. Specifically, we're exploring the link layer. We're going to transition from the clunky physical history of wired Ethernet all the way to the invisible dynamic negotiations of wireless LANs, or Wi-Fi.
And our roadmap today comes from some really fascinating university network engineering notes out of SLIT, specifically a lecture on the link layer, alongside a corresponding tutorial document.
Right.
What's great about these sources is they don't just tell us what networking is, they force us to look at the exact mechanisms of how devices figure out who is talking to whom.
Yeah. And the mission for our deep dive today is to demystify exactly how devices talk to each other locally. We're peeling back the curtain on what happens the exact millisecond you plug in a network cable or, select a Wi-Fi network on your phone.
Because whether you are downloading this audio right now or just sending a text message, the very technology delivering this content relies entirely on the exact frame-by-frame rules we are about to explore.
And I want to speak directly to you, the listener, for a second. If you are a university student prepping for an exam on this stuff, do not worry. We are acting as your expert academic mentors today.
Absolutely. Nobody is getting left behind. We are building this from the absolute foundation up.
So let's start at the physical layer, the humble beginnings. To understand why modern networks are built the way they are, we really have to look at the dominant wired LAN technology, which is Ethernet.
Right. The sources point out that Ethernet is simple, it's cheap, and it has kept up with an insane speed race, going from, 10 megabits per second all the way up to 800 gigabits per second today.
It's wild. It was co-invented by Bob Metcalfe, who actually sketched it out for the U.S. Patent and Trademark Office. But back in the 80s and mid-90s, Ethernet used a physical bus topology. We're talking thick, heavy coaxial cable.
Oh, yeah.
And there was a massive problem with this setup.
Yes, the dreaded collision. In a bus topology, you have a single physical cable acting as the shared medium. All the computers are physically tapped into this exact same line.
Just clamped right onto it.
Exactly. And because of this, only one host could transmit at a time. This is called half-duplex mode.
Okay, let's unpack this for a beginner. Imagine a crowded room where everyone is forced to shout through a single shared megaphone.
I like that analogy.
If two people grab it and shout at the exact same time, it's just garbled noise. Nobody understands anything.
That's a perfect way to picture it. In networking terms, if two hosts decide to send data at the exact same fraction of a second, their electrical signals physically crash into each other on the wire.
The electricity literally collides.
Right. The voltages sum together, corrupting the data, a collision. And as the network got busier, more computers trying to talk about, the number of collisions increased and network efficiency completely plummeted.
So how did early engineers fix a room full of people fighting over one megaphone? You can't just tell computers to be polite.
No, you literally have to hard code the politeness. They implemented a strict set of rules, a protocol called CSMAD.
Okay, that sounds like alphabet soup. Break that down for me.
Sure. It stands for Carrier Sense Multiple Access with Collision Detection. It is the medium access control protocol for early Ethernet. Basically, it dictates when hosts are allowed to transmit and exactly how to handle collisions when they inevitably occur.
So carrier sense, that means listening before you speak.
Exactly. The network card listens to the wire. If it detects a voltage, meaning someone else is talking, it waits. That's the carrier sense. Multiple access just means everyone is sharing the exact same line.
Okay, makes sense.
Now, if the line is quiet, the computer starts transmitting. But here is the genius part. While it's transmitting, it keeps listening.
Wait, so it's listening to its own shout to make sure it sounds right.
Precisely. That's the collision detection part. If it detects a voltage spike that doesn't match what it's sending, it knows someone else started talking at the exact same time. A collision occurred.
What happens then? Does it just stop?
It immediately stops sending the actual data, but it broadcasts a brief jam signal.
A jam signal.
Yeah, to make absolutely sure every other computer on the network knows a collision happened. Then, both computers that caused the collision back off and wait a random amount of time before trying again.
The random part is crucial, right? Because if they both waited exactly 1 second, they just collide again.
Exactly. It's called an exponential back-off algorithm. The more collisions happen, the longer the random wait times get, helping to, clear the traffic jam.
But wait, let me push back a bit. If everyone is sharing the exact same wire, how does your computer know which shout is meant for it?
What do you mean?
Like, if I'm shouting into the megaphone, how does your specific laptop know to listen while everyone else's laptop ignores it? I mean, the electricity hits every machine on the wire, right?
It does hit every machine, and what's fascinating here is how the data is packaged to handle that. That brings us to the anatomy of an Ethernet frame.
Okay, so packaging the data.
Right. The sender's network interface card, or NIC, takes the data, usually an IP datagram from the internet, and encapsulates it inside an Ethernet frame. Think of this frame like an envelope in the physical mail.
Right. The lecture notes break down this frame structure perfectly. It contained the 6-byte destination MC address, a 6-byte source MC address, a type field, the actual payload data, and finally a CRC or cyclic redundancy check to drop the frame if any errors are detected. Now, these MC addresses, they are hardware addresses, 48 bits long, written in those hexadecimal numbers separated by colons, like 0.8, 0.3F, and so on.
Yes. And there's a special broadcast address of all Fs, which just means, hey, everybody, listen up.
Okay, so to answer my earlier question, the electricity does hit every single computer.
It does. But when an interface card receives a frame, the very first thing it does in hardware is check that destination MC address.
So it reads the front of the envelope.
Right. If it matches its own physical burned-in address, or if it's that broadcast address, it accepts the frame and passes the payload up to the computer. If the address doesn't match, the NIC silently discards the frame.
The computer doesn't even know it happened.
Nope. It just ignores the shout entirely.
Here's where it gets really interesting to me, though. I was looking at the very beginning of the Ethernet frame structure in the notes. There is this field called a preamble.
Oh, yes, the preamble.
It's 7 bytes of alternating ones and zeros, 1010, 1011, followed by one final byte of 10101011. Why does networking require this bizarre, repetitive string of ones and Ls? Is it like a drummer tapping their sticks 1, 2, 3, 4 to synchronize the band before the actual song starts?
That is a brilliant analogy.
Yeah.
Yes, the preamble is exactly like a drummer's count-in.
Wait, really?
Yeah. Remember, in a physical wire, signals are just voltage changes. There's no separate clock wire keeping time. The receiving hardware needs a fraction of a millisecond to wake up, realize the signal is coming, and lock its internal clock to the exact frequency of the incoming ones and Ls.
So it's literally tuning itself to the rhythm of the sender.
Exactly. Those 7 bytes of alternating ones and Ls provide a perfectly predictable, steady wave for the receiver's hardware to synchronize its timing.
And what about that last byte, the one that ends at 11?
That final byte is the downbeat. It breaks the pattern. It tells the hardware, okay, we are synced. The very next bit is the start of the actual destination MO address.
That is incredible. A microscopic drum count-in happening billions of times a second.
It really is a symphony.
But, even with the drummer counting in and M addresses filtering the noise, the single-wire bus topology was still just too messy for the modern era. The collisions were too much of a bottleneck.
Far too much.
So the 90s brought a revolution, the star topology and active switches. This is where networks got smart.
Yes, moving from a dumb hub to an active switch changed everything.
The notes emphasize that a switch is an active link layer device. Unlike an old hub where all the cables formed one giant collision domain, a switch puts every single host on its own separate Ethernet segment, its own dedicated spoke.
Right. If we connect this to the bigger picture, the switch acts as an intelligent traffic cop sitting in the center of the star.
Okay, so how does it manage the traffic?
It uses a store and forward method. It receives the entire frame on one port, holds it in memory, examines the destination, and then forwards it only out the specific port where the destination lives.
So no more shouting to the whole room.
Exactly. Because each host has its own dedicated wire to the switch can talk to multiple hosts simultaneously. There are no shared wires anymore, so collisions essentially vanish.
So what does this all mean for the person actually plugging things in? The sources describe switches as plug and play and self-learning.
They are.
But wait, if I just buy a switch from the store, power it on, and plug 10 computers into it, how does it instantly know where everyone is? I don't have to program a directory. How does it know my laptop is on port 3?
It's a brilliantly simple mechanism. The switch learns by observing traffic. The lecture notes provide a great example of a self-learning multi-switch network.
Walk me through it.
Imagine host A wants to send a frame to host G. When host A sends its first frame, the switch looks at the source MAC address.
Oh, it looks at the return address.
Precisely. It says, MAC address. A just sent me a message on port 1. I don't know where it's going yet, but I'll write down in my memory table that host A lives down port 1.
It's building a map based on where things come from.
Exactly. But initially, that switch doesn't know where host G is. It's never heard from G. So it does what we call flooding. It copies the frame and sends it out every single other port.
Just blasting it everywhere, hoping it finds G.
Right. And eventually the frame reaches host G. Now, when host G replies to host A, it sends a frame with its own source MAC address.
And the switch sees that and writes it down.
Exactly. As that reply travels back, the switch updates its table with G's location. From that moment on, they selectively forward frames between A and G using only the necessary ports. No more flooding. Plug and play.
Okay, so we've perfected the wired switch. The traffic cop knows where everyone lives, but let's be real, modern devices move.
They do. Nobody wants to be tethered to a wall anymore.
Exactly. So we had to cut a cord and make the leap to wireless LANs, the IEEE 802.11 standard. And this brings us to the tutorial portion of the source material.
Right, the wireless questions.
And since we know a lot of you listening are university students prepping for exams, we are acting as your academic mentors today. We are not skipping anything.
Absolutely not. No one gets left behind. We are going to systematically analyze every single question from the wireless tutorial document in strict order.
Starting with question 1. And for every single question, we are strictly following a 5-step operational framework to make sure you score full marks.
I love this framework. Let's do it.
Okay, step 1. I will read the question word for word. Quote, question 1. Contrast ad hoc and infrastructure BSS architectures. End quote.
Step 2, source tracing. You will find the origin of this question right in the opening slides of the wireless LAN section of your CELI IT lecture notes.
Right. So step 3, our step-by-step exam strategy. If you see the word contrast on the test, the grader is looking for a direct comparison of a core feature.
Exactly. So your strategy here is to identify the central routing mechanism or the lack thereof and compare them.
Which brings us to step 4, delivering the final answer. What exactly do they write down on the test script?
You're right. An ad hoc BSS has no central access point, so hosts communicate directly with each other. In contrast, an infrastructure BSS requires a central access point that all traffic must pass through.
Perfect. Clear and concise. Now, step 5, our PhD-level deep dive with a real-world analogy. Let's make this intuitive.
Right, so think of an ad hoc network like a study group sitting on a campus lawn. Everyone is just talking directly to each other's laptops. No one is in charge.
Just chatting across the grass.
Yeah, exactly. But an infrastructure setup is like a traditional lecture hall. All the students or devices must direct their questions to the professor at the front of the room. That professor is the access point.
That makes total sense. Okay, moving right along to question 2. Step 1, read it word for word. Quote, question 2, differentiate between passive scanning and active scanning in AE 802.01, end quote.
Okay, step 2, source tracing. This is found in the network discovery section of the same lecture notes.
Step 3, exam strategy. For this, you need to focus on who initiates the conversation.
Right. Does the router speak first or does the laptop speak first?
So, step 4, the final answer you write down is, in passive scanning, the access point periodically broadcasts beacon frames to announce its presence. In active scanning, the host device broadcasts a probe request frame to actively search for available access points.
Spot on. And for step 5, our analogy. Passive scanning is like a restaurant with a neon sign flashing in the window. The access point is the sign saying, I'm here. Your phone just quietly walks down the street, reads the signs, and decides which restaurant to enter.
I love that. And active scanning.
Active scanning is entirely different. It's like walking into a crowded street and shouting, hey, is anyone open? And all the restaurants shout back with their menus. Your phone initiates the search.
Okay, that actually perfectly leads into question 3. Step 1. Quote, question 3. Explain the privacy implications of a directed probe request versus a null probe request, end quote.
Step 2, source tracing. This is the advanced spanning slide in the notes.
Right. Step 3, exam strategy. You need to focus on the SSID field in the request frame. Is it filled in or is it blank?
Exactly. Step 4, the final answer. You're right. A directed probe request includes a specific SSID, meaning the device broadcasts its connection history, posing a privacy risk. A null probe request leaves the SSID field empty, asking any available AP to respond without revealing past networks.
And for step 5, let's unpack that privacy risk. Because if my phone is constantly shouting into the air, asking for specific networks, isn't that a massive privacy leak?
It is a massive leap. Historically, devices would actively probe for specific networks they remembered.
Like, is John's home Wi-Fi here? Is downtown coffee shop here?
Exactly. Retailers actually used to use Wi-Fi sniffers in malls to track shoppers moving from store to store based on those directed probes. It was a privacy nightmare.
Wow, but the null probe request fixes that.
Right. It's the difference between shouting, "Is Mario's Pizza open?" versus shouting, "Is ANY restaurant open?" It protects your history.
That's brilliant. Okay, we have arrived at the final question, question 4. This is a practical puzzle. Step 1, reading word for word. Quote, question 4. A host wants to join a network named SLIT-STD. It sees access point A at negative 48 dBm, APB at negative 42 dBm serving SLIT staff, APC at negative 64 dBm, and APD at negative 52 dBm serving SLIN staff BYOD. Which access point does the host choose? End quote.
Okay, step 2, source tracing. This synthesizes the entire wireless chapter. It tests your knowledge of SSIDs and signal strength evaluation.
Step 3, your exam strategy. If you see this on the test, you need to filter the information logically. First, look at the network name, the SSID. The device specifically wants SLIT-STD.
Right, so you immediately cross out APB and APD on your exam paper because they are serving different networks entirely.
Staff and BYOD, so they're gone. Now you're just looking at APA and APC. Assuming they both broadcast the correct SLIT-STD name, you move to the second filter, signal strength, measured in negative dBm.
And here's the trick. Because it's a negative number, the number closer to 0 is actually the stronger signal.
So negative 48 is mathematically greater or stronger than negative 64.
Exactly. So step 4, the final answer you write on your test script is access point A.
Perfect. Access point A. And finally, step 5, our PhD deep dive. Let's visualize this. My analogy here is imagining you're at a noisy cocktail party looking for a conversation about a specific topic, your network name.
I like this.
You hear someone whispering about it across the room. That's the negative 64 dBm. Then you hear someone talking clearly about it right next to you. That's the negative 48 dBm. Obviously, you lock onto the person next to you.
That's a perfect way to visualize it. Your device is doing this mathematical party trick in milliseconds. But, we still haven't addressed the elephant in the room with wireless.
What's that?
Well, we talked about how wired Ethernet solved collisions by giving everyone their own dedicated cable to the switch. In Wi-Fi, we are right back to the megaphone. Everyone is sharing the exact same airwaves. So how do we not just have a million collisions in the air?
Oh, right, because we don't have dedicated cables anymore.
Exactly. And wireless radios generally are half duplex. When a Wi-Fi antenna is shouting data, it is deaf to incoming signals on that same frequency.
Wait, so it physically cannot detect a collision while it is transmitting?
No, the shout is too loud. It can't listen at the same time.
So if it can't detect a collision, like CSMAD did on wires, what does it do? Just assume the data got destroyed?
It shifts from collision detection to collision avoidance, CSM Messier.
Avoidance, okay.
It still listens to the airwaves before transmitting. But because it knows it can't detect a crash once it starts, it employs incredibly complex avoidance tactics. It uses random back-off timers before it even tries to send, just in case someone else is thinking about sending at the exact same moment.
And in crowded environments, it even uses a reservation system, right?
Yes, like booking a table. It sends a tiny frame saying, "Ready to send," asking the router for permission.
And the router replies.
With a clear to send, effectively telling every other device in the room, "Quiet down, host A is about to talk." Only then does the device send the actual heavy payload of data.
It really is a symphony, a frantic, microscopic, highly organized symphony going on around us all the time.
It truly is.
Let's briefly recap our journey today. We started with the physical, chaotic coaxial cables of early Ethernet bus topologies, where data collisions were an electrical reality.
Right.
We broke down the highly synchronized anatomy of an Ethernet frame, complete with its drummer-like preamble logging in the hardware timing. We explored the brilliant, self-learning logic of modern active switches.
Mapping the network by looking at return addresses.
Exactly. And finally, we decoded the complex, invisible negotiations of Wi-Fi, evaluating signal strengths, sending null probe requests, and carefully avoiding collisions in the airwaves.
And the relevance of this is absolute. Every single time you join a network, whether you are physically plugging a cable into a port or tapping a Wi-Fi name on your phone at a coffee shop, this exact sequence is happening.
It's incredible to think about.
MSC address filtering, switch table updates, signal evaluation. It is all happening in milliseconds, entirely behind the scenes, ensuring your data gets exactly where it needs to go.
But I want to leave you with a final thought, something to ponder as you look at all the connected devices in your house or office. We talked about how modern switches learn by looking at the source MCA addresses and building a memory table.
Right.
Now, MCA addresses are 48 bits long. That gives us about 281 trillion possible physical addresses globally.
Which sounds like an infinite amount.
It does. But on a localized level, as we move toward a world with billions of tiny Internet of Things devices, smart light bulbs, smartwatches, connected cars, individual sensors, and factories.
Oh, I see where you're going with this.
Yeah. What happens when the physical memory limits of these self-learning tables and enterprise switches are reached?
That's a very real concern for enterprise network engineers today.
Exactly. Is the 48-bit MCA address system and the way switches currently map our physical world infinitely scalable? Or as our networks become infinitely more dense, are we on the verge of needing a completely new layer of invisible plumbing just to keep the traffic flowing?
It's a huge question for the future of the link layer.
Something to think about the next time your phone automatically connects to a network. Thank you so much for joining us on this deep dive, and we'll catch you next time.